So good afternoon. Let's continue with where we left off. So basically, in today's class, what I wanted to tell you was I wanted to clarify some of the issues concerning the frequency with which you have to n repeat that particular issue that we had yesterday. So I was hoping that you would have gone back and tried out what happens when you. So that was exercise number 10, right? So when I basically right at the end, when I used reset underscore time step 0, and then with the same understanding that we had previously, if we calculate these average time values, then this one has to be the frequency and this one has to be how this is n every. So many inputs has to be taken amongst the 10,000 different configurations, and we take all the 10,000 configurations in order to perform the average. So when I did this and I looked at my RDF underscore gas.txt, I found two sets of information like what I should. One for 20,000. The next part 20,000 does not basically contain the header, so you might get confused that it's not printing out the next set of information. So it works out really fine, and I also, the best thing to do if at all you have such doubts is to run it for a small period of time and manually average it to actually see whether it is doing what you want. Okay, that's what I did for this, and it seems to be working perfectly fine. So our understanding concerning what these three values are was actually correct. Okay, so I hope you had an opportunity to try that yesterday. So today what we will do is we saw a couple of different potentials. We can keep talking about different kind of potentials and how to feed them into LAMMPS and how to make the input script read the information. But I thought today I will actually provide you with an input script that will essentially calculate the elastic constants of a solid. Okay. So what we are going to do is we are going to use the same idea, same intraatomic potential that we used for aluminium. Okay. And we are going to calculate its elastic constants, and obviously we need to be able to check whether the calculated values are close enough or not. So I am going to do some sort of a brute force method in order to calculate these elastic constants today, but the methodology that we are following is quite intuitive, so you will find it easy to understand. So this will be exercise 14, and I have a paper here where I have some document here which was got from the internet, so I will share this with you as well. And they have actually calculated the elastic constants of several metals and alloys using embedded atom method, and they have tabulated the values. So we will actually be using exactly this. If you remember right, the file name that we used for the aluminium intraatomic potential was also aluminium underscore jnp.eam, and these are the values of the elastic constants that we need to calculate for this particular material. So aluminium, as you might know, is actually a cubic material, right? So aluminium is actually a cubic metal. So cubic metal means it will have three independent elastic constants, basically C11, C12 and C44. So C11, C12, C44 are basically the elastic constants written in the White notation. So I hope you know what White notation is. This is essentially C1111, 1122 and 2323, if you will. Okay. So but for the cubic material, the relationship between the stress and the strain tensor can be written as equation number 45. So you see that C11, C22 and C33 are equal, C12 and C13 are all these things are equal. Okay. So this set, and then all these shear components all turn out to be equal for a cubic material. So using this constitutive relationship, we can design experiments using molecular dynamic simulations in order to determine these elastic constants. Okay. So if you take a look at the first equation that we can write, so what we can write, for example, is sigma 3 or sigma 33 is nothing but C12 times C12 times epsilon 1, C12 times epsilon 2 and C11 times epsilon 3. Okay. Suppose we keep the strains epsilon 1 and epsilon 2 to be 0. So, we constrain the box to not be expanding or contracting in that direction and apply only a strain in the z direction at a specific rate. Then C11 is nothing but sigma 33 divided by epsilon 33, provided the stress strain relationship is linear for the amount of strain that we have actually given, right. So, we need to make sure that we are going to deform this simulation cell very little, not too much. If you do too much, then you will have yielding and all that. So, that we can see all that as well. Okay. Now, with the same experiment, it is possible for us to say that sigma 2 with the same experiment with basically epsilon 1 and epsilon 2 constrained with only epsilon 3 applied. With the same experiment, you can also see that sigma 2 is actually equal to C12 times epsilon 1, C11 times epsilon 2 and C12 times epsilon 3, right. So, since epsilon 1 and epsilon 2 are 0, C12 turns out to be sigma 22 by epsilon 3. Okay, the slope of sigma 22 versus epsilon 3 will give you basically C12. However, for the other constant C44, you need to apply a shear strain. So, sigma 4 is equal to C4 times epsilon 4, or sigma 5 is equal to, sigma 5 means 2323, this is 13, sigma 13 is C44 times epsilon 13, and the sigma 12 is basically C44 times epsilon 12 or epsilon xy. So, we can do these simple experiments in LAMMPS in order to find out these elastic constants, and which is what we will be doing in exercise number 14. So, sigma xy, so x is one direction and y is two direction and z is three direction. Okay. Oh, okay. So, you are asking me why is a sigma 1 and sigma not sigma 1 1, is that your question, or?
I am just simply asking the meaning of 1, 2 and 3.
X, y and z directions. Okay. And we have used the white notation there to write that equation. You know the white notation?
I am aware of it, but I don't remember it actually.
That's fine. That's fine. So, basically it just it helps you to represent a second order tensor as a vector, right? The stress and the strain, and then you are able to represent the fourth order tensor as a second order, as a 2 by 2 matrix, as a 6 by 6 matrix. Okay. You can refer to any standard books on elasticity, you will find what exactly that means. Okay, it's very simple. Now, I want to focus on writing these input scripts. So, in this case, I am going to be deforming the simulation box in the z direction. So, as before, it is the same aluminum sample with the lattice constant being 3.986, which is exactly the value that gave us the minimum energy. I have just started off with that. I just started off with that configuration. Defined a region where the z direction has 20 unit cells, whereas the x and the y direction have 10 unit cells. Okay, created the region, created the atoms inside that region. I am saying what interatomic potential that I am going to use, and then defining the file that will contain that interatomic potential, and then I quickly minimize it. This step might not be required in this case, but what we want to do is we want to basically move the simulation box. So, now you imagine a simulation box which is 10 unit cells in the x direction, 10 unit cells in the y direction and 20 unit cells in the z direction. What we want to do is I want to move the top face, that is the z top face, by a certain amount, Okay. The command in LAMMPS which allows me to do that is basically the fix deform command. So, fix deform command is what we will be using. So, first what I do is I want to compute the stress. Okay. So, I say compute stress all pressure null virial. So, we will take a look at what that basically means. So, the compute pressure basically calculates the entire pressure tensor. Okay. So, it has an ID, it has a group ID, basically the total group of atoms over which you want to calculate that, and say pressure, and then you can say temp ID. Basically the temperature ID is the ID of the fix which basically calculates the temperature. Okay. Now the expression for stress from statistical mechanics looks something like this. It has a temperature term, okay, and this is the other term which basically just depends on the potential energy of the system, okay, or the forces, if the temperatures are not there, will only be due to the potential energy of the system. Okay. Yeah, Ri dot Fi. Okay. So this is the stress configuration, and this term, as you can imagine, is associated with the velocities of the atom, and these velocities are 0 when you are actually calculating the elastic constants at 0K, right. I don't want to calculate the temperature effects just for the heck of it, just to see how good our calculations are without including those terms. And as you can imagine, metals and ceramics may not show significant deviation from in their elastic constants unless and otherwise you are going to reach really high temperatures, right. So we are interested only in this term for now. So what I have to do is, it says here, give the ID of the compute that calculates the temperature and can be null if not needed. Okay, so I am going to say null. That's why I have given in that particular keyword the word null. Okay, and then keyword kinetic energy or pair or bond or angle or dihedral or all these things is given. I am just going to give virial. Okay, so basically the virial component of the stress alone is considered here. So basically the second part is going to be considered here. Say all the other terms actually don't make any sense for this particular case. Okay, you can, if there are dihedral angles or if there are angle potentials associated with your interatomic potential, then you would be able to calculate stress components associated only with that potential for your system. Okay, for now we just are going to give virial. Okay, you could try what happens with other things. I haven't tried it at this point. And then I am going to initialize the current length of the box, IL, and then calculate the strain to be LZ minus $IL divided by $initial length. So basically the current length minus the initial length divided by the initial length would give me the strain. Okay, and then I say fix. This is the fix ID, the ID for the fix. This is the group of all the atoms over which I want to apply this fix, and they say deform, and then I give how frequently I want to deform it. So every how many steps do I want to perform this deformation. So I say 1 there. Okay, can you all see this? Yes. And then I say in the z direction, and the delta, by how much do I want to extend in the z direction. So that is given by the keyword delta, and then the first and the second terms tell me how much in the z low do I want to increase and how much in the z high do I want to increase the length of the simulation box. So that is 0.0 for z low and say 1.5944 for z high. So 1.5944 turns out to be about 2% strain. Okay. And then I said all these units, distance units, is in the box units. That means it's in angstroms. And then I dump all the coordinates as it is performing this deformation, and I also print out the output of the compute command using the C_str1. It's an array, right? Because it's an array. It's a pressure. Pressure is going to be an array with 6 components because it calculates the pressure tensor. So the compute will have in str 6 components. This is the xx component, this is the yy, z, xy, xz and yz components. And then I am printing the variable which is a strain for that. As it is deforming, I want to print the variable, and I also have just plotted the lx and ly just to show you that that is actually not changing when I am actually performing this test. I run this for about 10,000. What this means is, this deformation of 1.5944 will be achieved in about 10,000 steps. So if you look at this calculation carefully, this strain is about 0.02 and the strain rate is 0.02 per picosecond, right? So 1, 2, 3, 4. So by not per picosecond, by per tens of picoseconds, right? In tens of picoseconds, because we have 10,000 here. So 10,000 multiplied by 0.0011, 2, 3, 4. So tens of picosecond, and this turns out to be 0.02 into 10 to the power 11 strains per second. Is that right? And that is a huge strain rate. So the reason why I made this simple calculation here is to show you that because of the time scales and the length scales that are actually involved in molecular dynamic simulations, whenever you perform such deformation experiments, is it?
0.02 per 10 picoseconds.
Yeah. So which is 0.02 times, so 10 picoseconds is 10 into 10 to the power minus 12 seconds. So it goes to the numerator and you get 10 to the power 11, right? So I think this is correct, right? So 2 into 10 to the power 9 strains per second. It's a huge strain rate, right? So these calculations, you can, for the sake of calculating elastic constants, this might not be very important, but when you are talking about plasticity, when there is deformation beyond the elastic regime, what will happen is your stress strain plot is a very strong function of the rate at which you are actually pulling this thing. You must have studied these effects a lot in your material science. So whenever you are interpreting results in molecular dynamic simulations, especially those pertaining to these high plasticity and yielding and all that, you need to interpret your results very carefully. Okay, and if you're going to do realistic strain rates, your simulations will never complete within a reasonable time. So you have to know how to interpret your results at least qualitatively when you are performing these experiments. Okay, so that is something that you need to keep in mind. So when I do this, I get since I am plotting the the entire stress tensor and the corresponding strain in the thermo file. So I will have that information in the log file, and I have actually deleted all the other lines which are not needed, and I got a file which only has the stress and strain information, and the last two columns of every row is 39.86, which is Lx and Ly, essentially clearly not changing, which means there is no strain in the other two directions, right? So when I read this file and plot it, exercise 14, so I am going to first somewhat I get a straight line. However, you see that it is not really starting at 0, but there is a 0 stress state at some sort of a positive strain value. Okay, so these are some of the issues that you actually need to fix before you actually start calculating your stresses. But let's see what happens when you do this. Okay, when I did this, the slope of this line turned out to be 106.4577 gigapascals. So let's check that paper and see what values they have. This is a very crude method. This actually takes a few seconds to run. It doesn't even take, it's not a long simulation. It's a very, very quick simulation. So you don't have to expect the exact value turning out here. 96.58 is the value that these guys are getting. Okay, and the actual value is 107.3 gigapascal from experiment. So we're actually closer to experiments than what this paper is telling us. Okay. Now what happens to C12? Okay, the C12 is also calculated in a very similar manner, except that I need to $79.971 is what I get, and according to this paper it is 74.61. So in this we are quite far away from the experiments, but closer to this value, right? At least it's in the same ballpark, at least it's in the same order of magnitude, right? Okay, from really simple calculations, something that runs very fast. So that's C11 and C12. The next thing is applying shear, right? So that is there in the no L underscore. So that's the calculation that needs to be done for a shear case. Okay, for shear deformation, the same fixed deform command is going to be used here. So I am going to be talking about certain important lines and then going back here and tell you why I actually did it this way. If you notice here the lattice structure is not defined just as lattice FCC $A, right? I am defining it like what I did for other crystal structures, and that's because my simulation box needs to be a triclinic box if I want to be able to tilt it in LAMMPS. Okay, so if the fixed deform command has to have a XY, so previously we had an Z here telling that I want the Z part, the Z direction to be deforming for the simulation box. Now I am saying the XY needs to be deforming, right? So if that has to happen, then what I am supposed to give is, so imagine this to be the X axis and this to be the Y axis. What I am supposed to be giving is the distance by which Y needs to be moved towards X. So basically this distance. Okay, that's what I am supposed to be giving in order to deform the simulation box and shear it. So XY means distance Y needs to be moved in the direction of X. That's what it means. XZ means distance Z needs to be moved in the direction of X. Okay, so you will find these things in the manual and it can be pretty confusing the first time you look at it. So the tilt, the extent of tilt that needs to be given to these axes is what is being given here. So let's take a look at the fixed deform command. So the fixed deform command takes an ID, a group ID, all here. Deform is the keyword or the style, the name of this command. N is every step, and then parameter can either be X, Y, Z, X, Y, X, Z or Y, Z. So what that means is, X, Y means, like I said, you need to give the value of the tilt, the distance, the second thing axis needs to be moved towards the first variable. Okay, that's important to remember. So how do you figure that out? So that also needs to be in angstroms. So what you can do is, so you take your MATLAB and then you say that, say you want a 3-degree tilt, right? So tan d 3 degrees multiplied by this y will actually give you this distance. So this y turns out to be 39.86 in our case, which is 2.0890, right? So that's the reason why I have here 2.0890 units is box again, and this, and what is that?
Low and high. Zero.
No, there is no low and high. This is just the total amount of tilt that you have to give for the xy. Only for x, y and z do you need to give a how much you want to push down in the x, how much you want to pull up in the x high, how much you want to increase it. But that also you see I gave this to be 0 and just increase this. So it's the same thing. They are just giving you an option to do that if in case that is required. Okay. So yes, it gave an error. Yes, that's right. You can't put 0 here because delta, for example, if you see x here, delta is d low and d high, whereas xy is just the tilt, right? It's just the tilt. Again, this also is done over 10,000 time steps, so it will do it in about 10 picoseconds. And I'm printing out everything here. So I'm printing out the stress, the epsilon xx stress, epsilon yy, epsilon sigma zz, and the strain in the z direction, and all the corresponding shear. This is what we are expecting to have non-zero values, right? We are expecting the xy shear stress and the corresponding shear strain to have non-zero values, which are the the 1, 2, 3, 4, 5, 6, 7th and the 8th column. So if you take a look at the so 1, 2, 3, 4, 5, 6, 7th and the 8th column. So initially the strains are small. Oh no, this is not right. Ah, no, edge xi is 14 only. So I just printed out all those values into another file and deleted all the unnecessary lines. So if you look at the this is the first stress, first strain, second stress, second strain, third stress, third strain, fourth stress, and the corresponding value of strain initially is 0, but in the next line if you see, this becomes, there is a non-zero value for these strains, and finally you reach the required strain. Okay, you reach the required strain. Again, if you plot this, you get a straight line. So that's C11, C12, and this is just C44. And then if you look at the corresponding value of P1, it turns out to be 46.3771. Let's see how we are doing here. 40.43. The actual value is about 28.3. So it's not great, but it's okay as far as the potential is concerned. So this potential is supposed to not do anything better than that. Okay, so you need to keep in mind what experiments are saying about your values and what this potential is capable of predicting. Now this is not a very amazing thing, because most likely these embedded atom potentials are going to be fitted for actually reproducing some of these elastic constants. Okay, so but in case you have an interatomic potential for which you don't know the elastic constants, to get the order of magnitude, you can do some simple tests like this to actually figure it out. And you have to make sure, and you're making sure every time that you're looking only in the linear portion of the curve, because when you're pulling, if you look at the extent of pulling that's going on here, I'll show this to you later, you can actually hardly see it being moved. It's actually being pulled now. Okay, so it's being pulled very little, so you cannot see it much. There's some little bit of movement if you observe very carefully. Okay. Can you see the box moved a little bit? No. No, wait, once it loads completely, it will appear to be a little bit fast. So it's more, right? Oh, I should switch this off. 1 minute. Now I think you should be able to see it move a little bit. Okay, and the shear thing also moves very little, but that is a little bit more, can be seen a little bit more clearly. You can see the box being sheared in the xy. The y is moved like what expected. The extent xy specifies how much y is moved towards x. So you see that it's that axis which is moving towards y by this amount. Okay, this information as to what xy, yz and xz means is also useful for constructing triclinic simulation boxes. Okay, So we haven't done that, but with that information you should be able to do it pretty easily. Okay, now what happens if you actually pull it even more? So how do we actually I'm going to exercise 15 here. I'll tell you what it does. Let's look at this. So the idea is to have a long nano sized, or not nano, some material with free surface. So this is the same copper material, except that now I have an outer simulation box and an inner region in which I am actually filling the atoms. So I am not filling the entire region with atoms, but something else. So simulation box is the outer part, and then there is another region within it into which the atoms are being filled. And now if you keep looking at it, it is being pulled, and it's not just being pulled. After every bit of pull, the energy is being minimized. Okay, the energy is being minimized, because if I continuously pull it, the pull rate is so fast that the atoms are not going to occupy their minimum energy positions unless I actually minimize it for every step of pulling. So you see that when you look at the deformation at some particular point of time, it's okay, but then all of a sudden you have the shear bands and all those things will start appearing. So in order to look at this a little bit more clearly, so what's basically happening is that there's slip, right? You've studied in material science, there's going to be slip. So you can see those slip bands somewhat. I'll take a look at this input file in a second, but if you do something called as the common neighbor analysis, so common neighbor analysis is a technique which is capable of identifying atoms belonging to a FCC or a HCP or a BCC or a icosahedral lattice. Okay, so if you just say perform common neighbor analysis, it is basically going to color the atoms depending upon whether they are a part of the FCC, HCP, BCC, icosahedral or other, something else. So if you take a look at this, everything else that's not in the center is marked as other, because they are atoms belonging to the free surface. So they will not be FCC or BCC, right? They will relax in a slightly different way. So if you continue to keep looking at the colors, all of a sudden you start, some BCC atoms begin to appear, and then you have some failure. Okay, so you can actually look at this a little bit better if you do select type, select the other atoms, that's the outer shell atoms, and basically delete them. So where is this? Delete selected. Okay, and then look at only what is happening to the FCC structure. So initially everything inside is FCC. For a particular value of strain, this is again a very simple calculation, very simple small input script, and you have the deformation. You have all sorts of shear bands and other things happening. So you see that 45-degree plane here, that's over which it is actually slipping. Okay, so you can see whatever you study in your book, you can actually see it happen when you actually simulate these simple things with LAMMPS. Okay, you can do a better job. I need to play with the input file a little bit more, but let me show you what the input file looks like, because this time it's just not enough if you just continuously pull it, because you have to allow these atoms, as you previously we just pulled it a little bit, so it didn't really matter, we were within the elastic regime, but now we are going beyond that. So for every pull you might want to make sure that the atoms are reaching their equilibrium positions for that stretch. Okay, only then will you be able to capture this phenomena. If you continuously pull, you don't see that. So so again I start off with the FCC structure and everything. So all the same, everything is pretty much same. But what I do here is I've introduced a couple of new things here. What do I want to do? I want to be able to apply some strain to the top face, minimize the energy, apply a little bit more, minimize the energy, apply a little bit more, minimize the energy until some finite strain is reached. So right now I am applying a total strain of 15.5840 divided by 79.72, whatever that is. I think that's a 20% strain, okay, and I am saying that the amount by which I want to extend my delta or of my simulation box in the z direction is 15.580 divided by 20. So I define a new variable which is this delta z times 1. Okay, so initially it is 15.5840 divided by 20 times 1, and I calculate a new variable n delta z and apply that to my fix all deform command. Okay, this label repeat is actually a label in the input script, so that I can use this jump command to go back here and re-repeat it for the next one, and it will add it to the actual value that it had reached previously. So if LEZ was actually the first length, and in the first step it did LEZ plus delta EZ, the second step when it comes, it has to do LEZ plus 2 delta EZ, LEZ plus 3 delta EZ. So that is the reason all this is 1, because I always have to add the same amount to the final length. So this could be actually modified and made a little bit simpler, okay, obviously. So, and I try to achieve each deformation, so each delta z is achieved in about 1000 steps. Following that, I minimize the command and I make sure that I unfix it, because next time when it goes back to the same, when it goes back to the loop, it will find a fix which was already defined. Unless I unfixed it, it is going to give me an error. Okay, so I unfix the deformation. So I do this, achieve a small delta z in 1000 steps, minimize the energy, minimize the energy, minimize the energy for about 20 steps. In about 20 steps, I will reach 15.5840 total delta z. And if you look at the, I have to see if my strain and then simultaneously I print the strain and the stress and append it to a text called strain.txt. So as and when it is calculating the stress and the strain, it is going to fill it up with this line. So let us see whether this, yeah, so it contains about 20 steps, about 20 steps, and if we actually plot it, you will see some non-linearity occurring, obviously. So it's just going up, failing, and just failed here. Something has happened at this spot. Okay, until about, in this case, until about 10% strain, you are not seeing much of yielding, which is that usual? No, it's not usual, right? You're looking at, this is happening because it's not the bulk material, number one. Number two, it is a single crystal copper. Single crystals are extremely strong, right? They have very high, and then you're also pulling it at a very high rate, no matter what you do. Okay, so all these things are contributing to this sort of a behavior, but you can see some failure actually happen when you plot the stress versus strain diagram. Okay. So these are some simple techniques that you can use in order to study the elastic properties of the materials. Now these are extremely crude ways. Now you can, there are more elegant ways by which you can actually define the elastic constants itself as a function of the velocities and positions of all the atoms in the system, and calculated using statistical mechanics. So once you know you have to print out the positions and the velocities, and then explicitly use that expression to evaluate your elastic constants of the material. Okay, so anything else? Any other questions? There's a dump here.
So LAMMPS PRG is something that wouldn't recognize.
No, it recognizes as soon as it sees the format. That's just if you used VMD, then you would have to give that. So I just gave it. You don't have to give it.
Sir, can you please show the script exercise 14?
The shear or the normal?
And 33 normal line where we are printing
Yeah, yeah.
those are lattice constants, those are elastic constants.
Which no, they are the stresses. So this is a compute, right?
The first three are
This is thermostyle. Custom means whatever I want to print, I will print. Okay. Step is the step number. Time is a time it has that has taken. C underscore str1 is
those are
taken
normal
from
stresses. First three.
first three are normal stresses. This next three are shear stresses, and then this is the strain that I calculate here. So in this in the next exercise in exercise 15, the strain is calculated in a careful way. So what is happening is, see, you have to think about it a little bit here. Okay, so when it comes to repeat, it is going to, this command is going to add the delta z value to the already expanded system. Okay, so to the already expanded LZ only it is going to add, right? But in the calculation of strain, the value that we want to subtract, the final length minus the initial length divided by the initial length, this is supposed to be the original 72 point whatever, right? The actual thing that we started off with, basically twice 39.86, right? So you have to store that value here. So IL equal to LZ and new IL equal to $IL. So when you do this, the new IL value does not change. It's fixed to the value that was initialized. Okay. So when you use the $new IL value, you will be subtracting it from 72 point something something, and here also 72 point something something, and this will be the new length, and you will get the corresponding epsilon ZZ. Okay, this is something that that I had to work with for some time to actually figure out. So sometimes you have to do some simple tests and make sure that you understand whatever this gives. Yes.
So we are having such high strain rate. So
Yeah.
like minimization will it happen actually like because of such a high strain?
No, I am actually applying a strain rate to deform it to a certain extent, and then minimizing the energy of the system. During the process of pulling, usually not much happens because I'm not giving any time for the atoms to actually move.
So
In a,
so won't the simulation be close to actual thing when we don't have the minimized effect during the iteration? Because it's so high that
it's so high, right? So in order to, if you, I don't understand your question. So you are telling me if I did not have the minimization, what would happen?
like since the strain rate is so high, minimization won't happen in the actual system.
Actual means in the real.
Like in the real case, the atom doesn't have time enough to minimize their atom.
Right. So this is not at that strain rate. This is not at that high strain rate. The total experiment is actually not on an average at that strain rate because I have allowed some minimization. If you want the total experiment to be at that strain rate, I shouldn't minimize. I just pull.
But the simulation itself is having such high strain rate, right?
This portion, the small portion where a delta Z is added is at a high strain rate. But then I stop it and minimize it, no. So that basically negates hopefully a little bit of that strain rate, high strain rate effect. Okay, the average experiment, the computational experiment that we have seen now, the overall experiment is not conducted at the high strain rate that you would get if you divide the strain amount by the time, because you are minimizing in between. However, this is a little bit more realistic of the real system than if you continuously pulled at such high strain rates, because you can't perform experiments at such high strain rates. So normally what we do is we actually pull a little bit, minimize it, pull a little bit, minimize it. So even though the elastic constant determination is, the methodology is very clear, the actual simulation can take quite a long time.
region in the script. We have outer.
Okay, good. That's a good question. I think I should have highlighted it. So here, there is a region. I say my region, block, and I'm giving some arbitrary values, minus 30 to 30, minus 30 to 30 in the x and the y directions. And in the z directions, it's exactly equal to 20 times the lattice constant, right? And then I fill another region, and I call it fill region because that is the region I'm going to fill, which is smaller than the outer region. But the ez direction exactly spans my box, right? Now when I say create the box, it creates with my region. When I say create atoms, I fill it inside this. So it just fills it exactly inside this. So now this is very nice because when you want to simulate, say, a sphere of atoms or put atoms in a cylinder, then you can always define this additional region and fill atoms inside that region. Yes.
What about the temperature, the initial temperature of the system? Does it minimize consider that? We're not defining anywhere the temperature.
We have not defined. This is just a pure molecular kind of static.
So what is the temperature?
0 K. Yeah, the atoms are not even vibrating about their mean positions in this case. But if you want more realistic elastic constants to come out of your simulation, you need to include those effects. Because the expression for elastic constants is not only dependent on positions, but also on the velocities. We have just removed that completely because we just wave our hands and say that for solids it's not that important.
So when you said it's calculating the pressure tensor,
Huh.
pressure is defined to be the isotropic part of the stress tensor, right?
No, it's not that. It's not the hydrostatic part of the. It's not hydrostatic stress. It's stress except that it is having negative. So that's why I added a minus sign in my stress here to make it appear positive, because all negative stresses means tensile, positive stresses means negative stresses in LAMMPS when it is printing out, it is actually printing out the tensile stresses, the stress that is acting in the other direction is negative.
Pressure is just calculating sigma.
So there is also a compute stress command.
That's compute stress per atom, right? We don't want that now. Per atom stress. Now what that means I don't know, but because you can think about it, what is meant by stress per atom? You still can get useful information. For example, if you model a grain boundary, and if you model the stress per atom and average it nicely, you will see the dislocation course alone stress. You must have studied that in some course, right? You have stresses emanating from the dislocation core reducing as 1 by r square or something like that, right? So you can look at all that. So this is actually the stress that's calculated per atom. But that's not what we want. We don't want per atom stress information. We want the stress for the entire simulation box. So it's a global quantity. So compute pressure is what is going to do that.